the whole world at our feet, watching seasons change. Our roads were lined with adventure, mountains in the way couldn't keep us from the sea. Here we stand, open arms. This is home where we are, ever strong in the world that we made. I still hear you in the breeze, see your shadows in the trees, holding on, memories never change.
Good evening everyone, and let's see if this actually works. If it does, then we can get going with tonight's topic. And I think it does. So tonight's topic is going to be VMs in reverse engineering, or actually anti-reverse engineering. Okay, I still need to mute myself on YouTube. So today's moderator is going to be KrzaQ. Here is his nickname. If you have any questions for me today, just ask him on either YouTube chat or on IRC, and he will let me know, and that way I can, well, answer the question. So, VMs in anti-reverse engineering, how does it work? It's basically a follow-up topic on what I've already chatted about, well, on the last couple of episodes where, as you know, we've implemented the chip 8 VM first and the first 3 episodes, and then in 2 more episodes which weren't really planned. It was all about the debugger for, well, that VM. Now, that was basically an introduction, so I don't have to explain to how VMs work. Now you know, or at least if you watched these episodes, then, well, you should know. And yeah, so I guess, well, one more thing, there's a mission today. So if you enjoy solving the missions, today's mission is brought to you by Foxtrot Charlie, and you'll probably enjoy it. Perfect. So let me find a text editor and we can get going with some code writing. Okay. Desktop. Perfect. So, what's the... Okay, let's do some theory first. What's the idea behind using VMs in reverse engineering? There are actually 2 ideas. The first idea is to, well, both ideas are the same in that you basically try to buy yourself time as the obfuscation offer, which tries to protect their application. You try to buy yourself some time against the person who is reverse engineering the application. Now, I'm not saying here like protecting or something like this, is seriously buying time, because with enough time, like every or almost every reverse engineering protection can be broken and will be broken. Unless nobody is interested in it, then it will not be broken, or you start going into some really weird physics, then it's an unexplored area, I would say. But yeah, so far history has shown that every interesting piece of reverse engineering technology was broken, so yes. So VMs are about buying time, and you can buy time either grabbing some piece of your functionality which you have in your application which you want to protect and actually creating a virtual machine around it, like implementing your own custom architecture and then reprogramming that logic from your from that protected part of your application into virtual machine bytecode, and then running it that way. So that's the first idea. The second idea is a little more broader. Instead of just protecting like one function or one module, what you do is you basically try to write a custom VM-based wrapper on the whole binary. And you can achieve it in a couple of ways, but in the end, it's still just an extension of the first idea. Yes, by weird physics, I do mean quantum computing, and I do mean some, like, well, really low-level stuff when you start operating on, like, single atoms or single photons. Cool. So today we will be basically implementing simple application and then a virtual machine in that simple application, and we'll see how it goes. One more thing, sometimes the virtual machines are well, you can use basically what you have. You can use the so-called weird machines which are on x86 already, for example. Somewhere on my blog, or if it's not on my blog, then I will post it later on. There is a KrzaQ where the KrzaQ itself was actually implemented in return-oriented programming, because that's actually Turing complete, which means you can do loops, you can do some other stuff. So, well, it wasn't a virtual machine per se, but in the end it was like reverse engineering. It was like reverse engineering a virtual machine, because you had to analyze the return-oriented programming of gadgets, and based on, you know, putting the gadgets together, you basically got bytecode of a virtual machine. And in that KrzaQ, it turns out that I actually implemented a virtual machine using this virtual machine, and that concept is called stacked virtual machines, where you actually, well, implement a virtual machine in a virtual machine in a virtual machine in a virtual machine. You get the picture. This isn't a new concept. I remember discussing this, or actually learning about this from like one of more senior reverse engineers on the Polish scene, from Bartosz, and that was years ago, seriously. So it's not a new concept, but it's a pretty interesting one, where you actually try to create a generator of virtual machines in such a way where you well, start with an outer one, but later on you actually like just run a script which generates a virtual machine implementation in using the bytecode of the surrounding virtual machine, and in the new internal virtual machine you do the same. You create some bytecode which is actually a virtual machine implementation, and so on and so on, and after you have like, I don't know, let's say a stack of 10 virtual machines, well, it becomes a pain to analyze it. And well, since this is a script, you can go even further, right? Now, that being said, an interesting topic from anti-reverse engineering is basically how to reverse virtual machines, and the approach is usually almost always the same. You can do some tricks, but the usual approach is first you need to realize you're dealing with a virtual machine implementation, and this is the most interesting and important part. I remember that on one of the first live streams which I was doing in English, I think, or maybe that was still in Polish, there was like a KrzaQ which I was solving, which was a virtual machine, and I was lucky to realize it was actually virtual machine just by looking that there was like a huge switch case based on bytes, where the byte would be an opcode. And yeah, once you realize it, then you have to do the second step, which is analyze all the opcodes, the bytecode of or machine code, if you will, of a given VM. And that usually is rather easy because nobody implements x86, where x86, you know, has like 1 million assembly instructions, and they have like weird registers and weird operations which do funky stuff. In custom VMs, usually people implement the basics. The basics meaning like addition, XOR, as in like some basic arithmetics, some basic logical operations, fetching from memory, putting stuff in memory, a set of basic general purpose registers, and some jumps which compare stuff solved in one way or the other. So knowing this, you basically know what to expect. You know that there will be like an instruction to XOR, there will be an instruction which does addition, there is one which does comparison, and a jump may be built into it. And knowing what you expect is rather easy to go just through the code and reverse engineer it, assuming that there are no additional obfuscations. But today we'll be only focusing on well, just the VM, but you know, usually it's good to combine these mechanisms. And well, knowing that, then there is the step 3. The step 3 is actually writing a custom disassembler, because, well, don't expect there to be tools or like IDA to support a custom architecture that's just created or even generated by some random person. So you have to write your own custom disassembler, and that is easier than it sounds, actually. Well, on my last live stream, you saw me implement a really basic disassembler for chip 8, and this is only a little more complicated. Because you usually want also to have like jump targets and for it to be two-phase, so you actually do see where the jumps are and where are the separate functions, and maybe you want to add some other logic which will allow you to easier analyze it. And then you find where the bytecode in the binary is for that VM and put it in your disassembler, and you get to step number 4, which is reverse engineer the bytecode. And that might be, well, depending on the size of the bytecode, either easy or a little more complicated, but the amount of time basically between, like, all the 3 steps is the time you bought, right? Because the 4th step is basically what the person would be doing anyway. The person would be analyzing the logic the person is interested in, right? So, but if you add VMs, the engineer would not expect that they would actually have to go through realizing it's a VM, then actually reverse engineering the VM and reverse engineering, well, and implementing the disassembler. So this is the time you bought, and yeah, and this isn't really about using VMware or using VirtualBox or QEMU in your binary, because that's that's kind of counterproductive. Even if you do it, then, well, it's still a x86. There are still tools for it, and the main reason here is that there should be no tools for the given architecture. Therefore, the reverser should actually write their own disassembler. So that's the basics of it, basically. Okay, so one more thing which I need to fix before we get going. I see I've broken the feed, and the feed must not be broken, because we will not see your questions. Okay, sorry, give me a second. As usually when I break a feed, that means I forgot a comma somewhere. So let's see where I forgot my comma. This is fine. Okay, so you may or you may not know that actually the layout which you see around here is it's basically JavaScript for a headless Chrome. Why is this thing failing? Oh, I have no idea. So you're going to see for a second my debugging window, which is this, and then okay. So does it say, or there is actually nothing there? It should work then, but why doesn't it work? Well, it seems it just doesn't like me. Oh no, I know why. Because I was recording a video a few days ago, and I actually commented out the part which is supposed to scroll the feed. Oops. Okay, here we go. And does it work? Yes, it works. And there's already a question, so why don't I see the question here? Okay, oh, there are actually 3 questions. Perfect. So, from Adrian, can you run Triton on it at the end to see how it deals with your implemented VM obfuscation? I have absolutely no idea what Triton is, in all honesty, so that probably means I will not be able to run it. Okay, let's maybe switch to desktop and see what is it. Triton. Reverse and okay, it's a dynamic binary analysis framework. Oh, maybe I did look at it at some point. Okay, that's quite... Yes, I did look at it at some point, but I do not have it installed, I believe. I'm going to note it though, and I am going to probably tweet about how it... After I don't want to start on the stream, so after the stream I am going to take a look how it worked. Thank you, Adrian, for actually suggesting it. Then, what do you think about the recent discovered vulnerabilities in Intel Management Engine? That's a good question. I didn't look through the vulnerabilities themselves, so that's one thing which must be noted. The second thing which must be noted is that people have started looking at Intel ME around, I don't know, 2007, 2009. I remember the folks from the Invisible Things lab had a presentation on Black Hat in, I think, 2009 about it. So it was long speculated that it isn't implemented securely, and I think Intel was always saying, no, it's fine, and it turns out it's not fine. So personally, I'm happy that it got a lot of attention, because that means someone finally will review it, and maybe we will either be able to disable it or get rid of it in a safe way, and maybe it will be not enabled by default. Since Java ran on JVM, did that made it easier to decompile? So is there a situation when you make the program run inside VM, make it easier to reverse engineer on the compile? That is a really good question. The answer here is that in case of Java, the bytecode, which is generated after compiling Java, is actually a simple stack machine. And if there would be no toolkit, one would have to write a disassembler for it. That being said, there is actually, well, Java is a, has been on the market for years now, which means a lot of people created disassemblers for it, and even assemblers. It's called, I think, Jasmine or Yasmin as the assembler for Java. Anyway, and then people decided, hey, this is actually, you can actually decompile it, not disassemble it, but decompile it into something which looks like Java and can be recompiled. And there is a set of really good decompilers which actually are able to grab java.class file and return almost perfect, Java code, which is both readable and you can, recompile it later. And tools for this have been available for at least as long as I am into security. So for years, basically. That being said, the same is not true for a custom architecture where probably no tools are available apart from generic tools. Okay, so you could trace, the best supervisor says, you could trace the instructions still, and in the end the binary ends up being translated by the VM. This is a really good remark. Yes, there are a couple of tricks which you can do. This is the first one. You can trace the instructions and actually see what is executed in the end. It's kinda a little harder later on to, take out what's actually the implementation of like the VM, what is the added code, and what are the actual operations. And it doesn't make it easier to read. The other thing you can do is you can look at the memory. The memory usually is not encrypted, and when you find the region where there are the registers and the memory used by the VM, sometimes you don't care about the implementation itself. You just do basically like a side channel analysis where you look at the memory, look how it changes, and based on that and based on maybe changing the memory a little here and there between runs, you can also analyze whatever is going on inside. So yes, there are tricks which can help you, and obviously there are tricks which can try to prevent this. So it gets it's like a deep topic, and today I'm going to only talk about the basics. I'm actually going to implement it in C today, not in Python, not in something else, just in C. And though there might be bits and pieces of Python anyway. Cool. So I'm going to call it, I don't know, I said C, I'm going to do it in C++. Or like my favorite, flavor of C with classes. So what is the application going to do? Let's make it crack me, because why not? I mean, crack me's are usually a good way to demonstrate stuff. So I'm going to only make the VM will only be used for hiding the main logic, and the main logic in case of this application will actually, the main by importance, not by the being on the top. It's actually going to be checking the passphrase which is entered by the user. So all the code which actually grabs the input from the user and outputs stuff. This is going to be done well without outside of a VM in normal C++. There's another question. Is there a place that I can read more about creating a virtual machine or about this topic? In all honesty, I don't know. I mean, I'm basically going, this topic is from my head, as in I didn't do any research before the stream, so I have no idea. It's just like pretty basic fare in reverse engineering, I would say. So I'm sorry, I have no idea. That being said, if anyone on chat has any good links, then please do share them. And on YouTube, I think you cannot type the whole link. Like, try to work around it. I try to disable blocking links on YouTube chat, but that doesn't seem to work well. Okay, 2 more questions. I've read on some website that Intel ME is not only responsible for remote management, but also for a bunch of thermal management, fan control, OC, etc. Is that true? I actually have no idea. So I don't know. Maybe. But I don't know. Maybe the same chip is responsible for it. I'm not sure if the management engine, so no idea. It is a just question. And Matthew asks, how are kernel functions virtualized? Are they dynamically loaded from somewhere? What do you mean by kernel functions in this case? I mean, you basically use the same approach in user mode and kernel mode in case of application or driver level obfuscation. Unless you mean something else, then yeah, please let me know. Okay, so some random stuff. String. No, I am not using cout or cin. No way. Okay. Yeah, let's do like this. Let's do a key this time, not a password value, but a key. That's good. Let's do this. Here I'm going to actually call check, like check NVEnt. Obviously I first need to grab this. So if scan. Okay, and I guess I'm going to grab just a string. So the string is what is going to be the length of the key. The length of the key is going to be 16 because I say so. Key. So the size of the array is a little excessive, but I'm going to leave it as is because why not? If it's not equal to 1, then just bail out basically. Bye. 2 and 1. Okay, here I'm going to call check, and the check will return like there's going to be like a boolean value. Let's call it like key valid, maybe. And if the key is valid, then I'm going to say yup. Otherwise, I'm going to say nope, which is pretty, I guess, pretty standard in my case. Nope. Okay, and I exit. This is fine. Okay, perfect. And now I just need to implement the VM. Before I do that, I'm going to create a makefile. Because why not? Gs++ wall w extra. I'm going to make a makefile because I'm actually going to have a Python script which probably is going to compile some bytecode and put it somewhere in memory, so we'll see how it goes. And what is it called? appcc up. Okay, this is fine. Now I guess I can run it. It's going to complain probably about the boolean values uninitialized, and so it should. Okay, but it should still compile, so it runs. I need to enter something. Okay, yes, it's fine. I guess I'm going to do some checking here as well. Or am I? No, I'm not. Given that I zero this array, yeah, I'm not going to do any checking. Is this vulnerable? It is not vulnerable. This is actually the size of a buffer, so this is fine. It's okay. If I would omit the 16 here, that would be a buffer overflow, basically. That's a good question, David. Now, okay, a virtual machine. So how am I going to do a virtual machine? I guess I'm going to do a... This is, well, similar to what I've implemented already in chip 8, right? But simpler. So public. Yeah, I think everything is going to be public, because why not? Now the size of registers. Oh, before I get there, let's do std_end.h. Yeah, how will this work? I don't know. I'm going to, I guess, create 32-bit registers and operate on them, because why not? So, and this virtual machine is going to be like super easy. It's going to be really, really easy. So, here and 32 registers. I'm going to have 16 registers, because why not? I'm going to zero them. And then there's going to be a PC register, which is also zeroed. And then there's probably should be like some memory for it. Okay, sorry, not .h, yeah. Okay, and this is like the password, the bytecode, which is, oh well, the code, let's call it code, mem for memory, obviously. Yes, and now I need some, well, you know how it goes, right? I need some implemented instructions. This time, in chip 8, I actually did like a separate function for each instruction, or separate method. Now I'm going to actually do a huge switch case, because why not? So, yes, I'm just going to, I guess, create a method which is called check, and it gets not a string, it gets a character array key. Yeah, because why not? This is just an information from me that this is, I should expect 16 bytes. It's by no means actually, it's just, you know, a standard pointer to a char, whatever. Okay, now I am probably going to do something like this. Bool and equals false. While it's not the end, I would like you to yes, I would like you to exec one instruction, and this actually returns whether it's the end. So this is fine. Now return, I expect that the result will be in the first register, so I'm going to cast the first register to a boolean value, which is okay. And here I actually need to put the key in either the memory or in the registers. I guess I'm going to go for the registers, because why not? So I'm going to memcopy. This is quite funny. I don't know. It's probably undefined behavior what I'm doing now. Do I care? I absolutely don't. Key plus 0 for, okay. So first 4 registers are going to receive the key. Okay. Now I do believe I do need stdlib because memcopy is there. There's a question. Przemysław says, I of course meant that the thermal management is on the same chip and not the same piece of software. Yes, that makes sense. For example, in the Toshiba laptop research, which Redford and KrzaQ presented on Security Pwning conference 2 weeks ago, they analyzed that chip, which was the embedded controller, and it was handling everything from like BIOS password recovery through keyboard to being a keyboard controller and a couple of other things. So it's pretty much expected that it might be the same chip. Okay. Those memcopy are well defined. So I'm not sure if this... Basically, KrzaQ, so you're better in the standard than I am, but what I remember is that you are able to copy a piece of object from memory as unsigned cars into an unsigned car array and the other way around, assuming that it was in the beginning the same object. Well, here it's not, so this is probably an implicit cast or like a... Yeah. I'm not sure if it's well defined, but okay, if you say it's well defined, then I believe you. Now, as you can see, I also have like another function here, which is execute an instruction, and it doesn't take any arguments. Neither of these is actually const, because I might be changing the memory, because why not? Okay, so VM, and this is where the huge switch will come in. So, well, it's not going to be huge, by the way. PC, yeah. So switch over this and actually even iterate to the next instruction, to the next address. Or do I want it to iterate? No, maybe don't iterate. Just, yeah. Yeah. So, case, and here's the moment where I actually need to figure out, hey, what will be my instructions, right? And just for calculating this key, I'm going to use, let's say, I'm going to use, because it's going to be a key, not a password, like key as in it can, multiple different values of a key can be still correct. So I'm going to implement AND and XOR and probably something like 3 more instructions, and that's going to be it. So I'm going to start with 0, 0, because why not? And this is going to be, I'm going to treat it as XOR of, and it's going to expect 2 arguments. There will be like destination and source, where the source is actually like both our registers. Okay. Now, I'm going to do something funny, because I want this implementation... Sorry, the implementation doesn't have to be super safe, because it will never be running any bytecode, which isn't basically built into the application, right? And it's assumed that, well, the creator of application is actually the same person who is writing this bytecode, so it should be fine for me not to do any protections here. So I'm actually going to do something like this, and like this as an absolutely no bound checking. There will be like out of bound accesses to memory everywhere, but again, the attack model here is that we don't care. We just don't care. We assume this is safe. If it's not safe, then probably somebody could just modify the executable anyway, and there you have it. Cool. So given this, we get 2 registers. How should I do it? I should do it like this, maybe. Yeah, let's do like this. It's a little nasty. It's not really a, you know, a block. Well, it is a block, but not a, like, not in, like it in an if. Cool. So I get like to... no, let's not make too verbose instructions. This is going to be exert with PC plus 2. Yes, this is a pretty nasty code. And I'm not sure about this break. I think I'm going to do... No, break is fine, Yeah. Actually, no, because return is even better here. Let's just put it here, return false. I will return true only when I actually, well, want the VM to stop, when the VM finishes. So question, can we do Pawn Adventure next stream or one of the next streams? The RPG game thing, probably no, because it was in C#ish, and I'm not really good with C# tools, so I would prefer not to do it on the stream unless there's like a lot of people asking about it. Yeah. But actually, Foxtrot, if you could add this to... Oh, I don't know if Foxtrot is here, I'm going to paste it to him. If you could add this to the topic lists. Okay. Good. It would be pretty fun to play with that. Though a lot of people would come and would be like, oh, can they switch to actually streaming the video games? So this is fine. Now, I do want and here as well. What else do I want? Do I want any immediate value? Like, sorry, loading an immediate value into register. Let's say I want, but do I want it now? Yeah, I want it now. So it's going to be, I don't know, move, and 32-bit immediate value, which is going to be a memcopy. Memcopy to the register, which is pointed to by this funny expression, and from memory PC plus 2, and actually 4 bytes. Yeah. And this means, oh wait, this is an error, this should be 3 because there's an opcode and 2 arguments, so that's a 3. 3 here, and here's like opcode, 1 argument is 1 byte and the other argument is 4 bytes, so that's actually 6 bytes. Let's do it here, and I guess I'm going to do... I'm also going to do a move reg with a reg, yeah, like this. Okay, and this is obviously a 3-byte expression. Then I guess I'm going to do another one. This should be almost enough for me to do... Yeah, I think it's almost enough. With one more instruction I can actually implement some not great, but like really simple key checking. Okay, this is like end, done, finish, quit, whatever you want to call it. And what it does, it actually doesn't move the PC, it returns true. Otherwise, I want to return... I don't know, otherwise like, it should never get here. Yeah, let's do this. I can abort. Okay, now I need one more instruction here, which is bitwise OR. And this should be enough to... Yes, this should be enough for me to actually implement a decent... Well, not decent, like a basic key checking. And I think this is actually this is actually enough. So next thing I need to do is I need to write an assembler. Doug asks, do you really need all logic operations? Won't you use NAND or NOR? No, I just need, I mean, these three should be enough for basic key checking. I will do something like this. I will, like, assuming that each 4 bytes of a key is something I will call the part of a key. So I will probably XOR 2 registers with each other to make sure they have some value, and to check if it's that some value, I'm going to XOR that value with it. And I'm probably going AND to other registers with some other values, and expect that all the bits which I selected are, for example, 0, and then I'm going to OR everything, so I expect that it's 0, and then I'm going to XOR it with FFF, which is actually a bitwise negation, like two's complement. So yeah, so that's it. I mean, this should be enough to do it. I don't think I need any more. But I do need an assembler. So, how do you create an assembler? You don't. That's the answer. You actually use NetWrite assembler, and you create macros. So, these macros are going to be rather easy. I need a prefix. I don't know. I usually use V. So VXOR, VXOR, and I never remember the syntax. Let's forget this. NetWrite assembler macros. Multi-line macros. I don't need multi-line macros here, I believe, but single line. Yeah. Or maybe multi-line will be better. So, yeah, okay. This is perfect. So, macro, and this is how many arguments. I wanted to have 2 arguments, but I do want to use registers, and my registers will be called VR, like, I cannot use just R because, well, x86 has like R8, right? So I cannot use it because it would collide. I can use like VRO, for example, and this would be 0. And I have to do the same for all the 16 registers. I'm probably not going to even use 16 registers, but whatever. So yeah, let's just go with 7 registers now. This can be always changed later if I need it. This has 2 arguments, and I do need like an AND macro here as well. Macro, that's not the same word, is it? Okay. And yes, now I emit using db, which means emit a byte. I'm going to emit the byte. The byte is going to be 00, right? Because this is the byte. Then I'm going to emit the first register, which is actually the first argument, which is this. Well, yeah. And then I guess I'm going to emit the second argument. So I can even write it like this. And now I can write like the XOR VR0, VR1, and it will work correctly. It will compile to correct bytecode. So yeah, this is how you cheat creating an assembler for your language. You just create macros basically for NetWrite assembler or whatever else. That being said, I cannot, for example, do these 2 things need different names. So let's call it like move I as in move immediate. Move I, and the other one is move. Does move without anything. And the last one is just end. It doesn't have any arguments. And usually, you know, it use like the HLT hold, but and it's fine. So this is it. Now for moving the registers this is fine. Moving the immediate value is kind of different because the second argument is actually an immediate value, right? So I need to use DD because it's a 32-bit immediate value. Then everything else is fine with, as long as I fix this, and I do need to fix this as well. This is already fixed. And that's it. This is like basically the full definition of my new assembler language, so I can write the bytecode. Keycheck.vm, I don't know, vmasm, nasm, whatever, vasm. Vasm sounds like a perfect name, and I guess I'm going to do this. And I need to split the window. Perfect. Or actually change it. Yeah. So I have my macros here, so I can just take a look if I need to. Include vminc. Now, there will be no jumps here. This virtual machine actually doesn't have any jumps. I could add jumps, I could add a lot of more instructions, but just for the sake of the example, that's not really needed. So I am not going to do it. And I guess on the like chip 8 implementation, you already saw how to handle the control flow instructions. So, how to do the math behind the key? Let's do it like this. There are 4 pieces of a key, and I would like the last bit of the key and the first part of the key, so key 0 and key 3. Each of these parts is actually 32 bits, so please remember that this, when I'm writing something like this, I actually mean 4 bytes, I don't mean 1 byte. And I want this to be lead code, because why not? Then I want K0 and a mask. Let's use a mask like this. 1 4 1 4 1 4 1 4 has to be equal. Everything has to be equal 0, and then K1 or K2, I want it to be equal to FF, 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 FF. Yeah. So this way, actually, I can have almost any values here. So if this would be I don't know, a licensing piece of software, right? Like a check, which something who checks a license, I could still give different customers different numbers, because this actually has there are a lot of solutions which do meet these requirements here, these constraints, and I don't want to just boil it down to only one solution, because why not? I want it this way. I want there to be multiple solutions. Now I need to implement it, and given that I actually need K0 here as well, then I cannot write the result to here, so I'm going to do vmove to, I don't know, VR5, for example. I'm going to move VR0, and now I'm going to vmove VXOR that with VR3, because as you remember, obviously I do have the pieces of the key already in these registers. I might actually change the names from here from R to VR, but that doesn't matter too much. So yes, now I exert it. Now I'm going to load into VR6, let's say, the magic value, and I am going to XOR VR5 with this magic value from VR6. And what I expect here, if it's good, then VR5 is supposed to be, 5 is supposed to be equal to 0. Because, you know, XORing two identical things is 0. Well, that's basic of assembly. You probably saw millions of times something like this, which is just zeroing the register. And this will work that way as well. So this is the first part. Let me copy it here. Now the second part. And I still cannot move that there. So vmove, I'm going to note that result 1 or result 0, whatever, is in VR5. Okay, then I move to yeah, let's reuse VR6 because why not? This value and vent VRO with VR6. And if everything is good, then VRO is actually supposed to be equal 0 at this point, so result 1 is in VR 0, fine. And here I just OR it, there is no magic here, so VR1 and VR2. And I do need to load this magic value, I will need it later too. VR6, the value. And yeah, and now I need to XOR it because I want zeros if stuff is correct, so I need to XOR it with VR1 with VR6. And I expect if the result is correct, then, so if after this operation I actually get in VR1 only Fs, and then I XOR it with only Fs, then I should get 0. So VR1 is supposed to be equal 0, and the rest 2 is in VR1. And now in the end I need to combine all the 3 result registers together using OR. And I still want to have 0 there, this is because all of them need to be 0, right? So I do VR5, let's put it in VR5 because why not? Okay, and now I'm going to again XOR it with the XOR with VR6, VR5. Is this a good? No, I don't want to XOR it. I'm actually going to go with no, I'm going to change it in a different place, and the end. That's it. So here I actually expect that if it's good, everything is good, then VR5 is actually supposed to be 0. Though I did expect the result to be in this register, so I need to move it, vmove VRO and VR5, perfect. Now we have here 0 if it's actually correct. And non-zero if it's not correct, but a boolean goes the other way around, so I'm going to do this. Which is a standard negation, obviously, and now I need to check it. And to check it, I do need to, well, do a couple of things. First of all, I do need to put some bytecode inside this. So I need to compile my bytecode, put it in the memory, and then actually run it. So I'm going to create a VM, and in the end I'm going to call vm.check. And I'm going to pass the key there. Even if somebody like puts 1 byte here, well, the array is still 0. This is like zeroing the array, and the array is pretty huge. So there will be 1 byte and then zeros, and that's fine. But nothing will break. Okay, and that's about it, though I do need to put stuff in the memory. So I need to compile the bytecode. This is the first stuff. And to do this, I just need to run nasm on this key check. Nasm include expects a file name. I guess you want this. This is fine when it compiled, and we can check in a hex editor how does it look like. And it looks like, yes, it looks pretty hexadecimal. That's perfect. Now I'm actually going to grab my makefile and add the nasm line var keycheck wasm, sorry, and it generates obviously a file named keycheck without anything else. And now I'm going to use the funny trick with actually changing the keycheck into an object file, being a compiler's or linker's object file, and then I'm going to link them together. So I actually need this to move it here. To do it, I need to find this, my favorite snippet of code to do it. Okay, here we go. Okay. So this is the way you do it. I have it noted down actually. Object copy, and we grab as input. No, this is the type output. It's px8664 binary. True. Okay, and then I put the name of so key check and the name of the object file key check.o. So let's make it. That's okay. This is like some typos in my but it happened later, so I don't mind. Now it actually generated this this file, and this file contains somewhere here, I don't know, probably starting somewhere here and ending somewhere here, is the bytecode from that file, but it also exported two symbols. One is called binary keycheck start and the other is called binary keycheck end, and there's also another symbol called the size. And in my C++ program, I can actually access these global variables, because from a C++ perspective, these are global variables. So this is like a correct way you should embed data in your C++ application if you don't want to patch it. And I do have also, I believe, a piece of code. Yes, I'm going to copy paste the macro, which I invented some time ago. Invent is like trivial, obviously. Yeah. And this is a way to get the data into a string. So import the data string, blah, blah, blah. And this is the name, which is bytecode. Yeah, it's called bytecode. This is the name of a global variable. And I do need to check again, how is it called? It's called binary keycheck. And start and end are going to be appended, so yeah. And this will give me the bytecode here, so I just need to basically copy paste it into a vector. How do I even do it? I know, there's probably a smart way to do it, and I probably don't know it. Let's do it like this. I'm going to reset mem, resize it, sorry, to 4096, because that's a nice number. Now I'm going to mem copy to the beginning of it. Well, whatever that was called, like bytecode. Yeah. Data. And I'm going to copy bytecode size of data. Okay, and this is fine. Now, now it won't compile because what I did is I forgot to add the key check.o here. I'm going to answer questions in a sec. I see there are already a couple of them. So, CLS, oh, do I have string imported? I probably don't, so that might be one of the errors. Okay, CLS and make. Oh, it compiled. Well, okay, if it compiled, then that's fine. Let's see if it works. Enter your key, ASDF, nope. Well, probably nope, because I do need to write a key generator that actually generates the correct key, so I can test it. So let's go through the questions first. From Dima, can you briefly describe your hardware specs for security research reverse engineering? Yeah, sure. I have, what do I have? Let's see. Does this? Yeah, oh, this is fine. So I have Intel Core something at 3.2 gigahertz. This actually is, yeah, this actually is like 16 logical cores. So it's 8 cores, each can do hyperthreading as well. And I have 128 gigs of RAM because I don't like when RAM, finishes, ends. And apart from that, 4 LCDs because I actually do like, I like a lot of screen space where I can move my windows. I did try using one LCD, which is larger, it doesn't work for me. It's obviously per person, like person specific. And apart from that, well, I do have a mouse. This is a Logitech gaming mouse, and I have also a Logitech gaming keyboard, which, because Office standard default cheap Office mouse and keyboard just don't work for me. I use them too much to use like the default Office stuff. They just don't work for me. I guess maybe that answers your question. Yeah, plus I have some obviously hard drives, like an M.2 disk for fast stuff, and SSD for the operating system, and LEDs. That's the most important part, obviously. Are you able to solve this with symbol execution, or is it not possible for some reason? I think you might be able to solve it with symbolic execution. I don't believe I have Matic or Anger installed here, so I am not able to test it though. Okay, Duga asks a good question, a valid question. How do you want to translate x86 assembly into my RISC machine? Well, I don't, because as you've seen, I've written my key checking part, well, in the bytecode of that virtual machine. But your question is obviously, as you know, it's a good question. And the way, if you would insist on doing it, the way you could do it, I think the easiest is, well, don't bother. As in, don't bother with x86 code, but for example, write a module for LLVM, for Clang, and compile your C code into directly that different architecture. Or if you insist on actually grabbing a binary and translating it, you can translate it to an intermediate language, like for example OpenRail, or you can use, I guess you can also, there are some translators from x86 into LLVM bytecode, I believe. I'm not sure about it, but I think there are. And I've seen some research which uses them, but I don't know if they are public. Let me put it like this. And yeah, and move on from there using the same way, like have a transpiler or a compiler from that intermediate language, which is way, way, way easier than actually x86, because it has, you know, fewer instructions, and translate that into your bytecode. And this is the way I would actually go about it. What about the addition, subtraction, and so on, and other instructions? A just question, that being said, it's not really, it's copy pasting this and changing this symbol to different symbols. So it's easy to do, therefore I'm not going to do it on the stream, because, well, if you need it, you can just do it. There is no additional thought that you need to put into it. You need to put, obviously, some thought into, stuff which is not here. For example, what do you do if there's an integer overflow? Or if you actually have a division by 0, what do you do then? Sorry. So yeah, these are the questions I'm avoiding. And in this kind of a virtual machine, you can ignore it. You can choose to ignore it. You can do some other stuff. On division by 0, you can actually put some funky value in some register, or a random value, for example, because why not? So yeah, like imagination is basically the boundary. Now I need to write the keygen to check if it works. So asdf.py, because I'm going to write it in Python, obviously. Maybe not asdf. It's called gen, like for generator, or gen in that case. Where's my mouse? Okay, how do I want to go about it? How lazy am I? Let's say I'm really lazy. like this. So yeah, I don't even want to implement it, I want something else to calculate the proper value for me, as you can see. I do hope this is the order of operations, but just in case. And yeah, and this should be fine. One more thing, because the key actually needs to be yeah, the key actually needs to be ASCII safe. So how do I even K of extract, and now it's supposed to be like this. J plus 7 times J. Okay. V has to be more than more equal, no, more than 21, more or equal to 21, and V has to be less than or 7e. Okay, and this should be fine. Okay, this as no, not as hex actually, as long as hex and a string code hex. So yeah, I'm using a SAT solver, an SMT solver actually to generate my key, because why not? Now I actually need to, I don't have Z3 on my Linux, on my Windows machine, I have it on my Linux machine, so Python generate unsat. Okay, this is not good. Let's see what actually, because the other part, the part upstairs is satisfiable. Oh no, this is not hex. This is better. Okay, so this will be fine. Yeah, it's satisfiable, but it's not printable. So what do I do to actually make it fully satisfiable and printable? Is my math here okay? I am extracting from the top seventh bit here 0th bit plus 8 times j, so I'm extracting a byte from k of I, whatever is k of I, and I'm making sure that it's actually more than 21 in hexadecimal but less than 7e, which is the ASCII range. So this is fine. Can I actually do it for like only one register? Yes, it's doable for one register, it's doable for two registers. Is it doable for three registers? It's not doable, it's unsatisfiable, so I need to change my formula. How do I change my formula? Let me think. What's the problem actually here? That's the good question. Oh yeah, if I change my formula here to this, then it can be ASCII, because this is, I think, the only problem. For ASCII, no, this is also the C. Here and D here are the problem, because I need a top bit somewhere to be set to actually, well, do it. So for it to actually work. So I'm going to change it. So here's 1337. This will be fine. 1337. Then here it's this. Okay, now it's fine. Now it should be actually satisfiable. So let's run it again. And it is satisfiable, but well, what? Are these zeros? What are these? Because I actually neither space nor tab should be here. What are you doing? Hex dump dash C. This is 2 and 16. How can you be 16? You cannot be 16. I just told you not to be 16. Why are you 16? Oh, because, yeah. Okay, my bad, sorry. Okay, let's try it again. Okay, and this should be the correct key. So, well, let me maybe do it, print it in one line so it's easier to copy paste. No, this is exactly not correct. Okay. And let's see if it works. Nope. Okay. Because I didn't recompile with a change formula. That might be it. Still nope. Oh, come on. So this is where we reach the debugging part. Did I save this? Let's remake it. Run it. Copy paste. Nope. Let's do the math manually first, and well, I guess if I would ask this to evaluate it in the model for these values, it's going to tell me, yeah, everything's fine, but let's maybe do it. So print model eval k of O with k of 3, and I want it as long, and I want a hexadecimal value of it. No, sorry, this is wrong console. So this is sorry, this is fine. Now this should be fine. Since I'm debugging, what I can do is I can actually put, with each cycle, I can put the register values out, and this should help me debugging a lot. So printf, no NDNS issues. No, these are only bitwise operations. There should be no NDNS here. Or maybe, let me think, maybe you're right. But no, if I recall correctly, this actually uses little. No, it doesn't use little NDN. This is actually already the values that are coded. It doesn't think with bytes. So no, this is fine. It's probably not NDNS issue. For int I0 then how many registers am I using there anyway? I think 7, right? Well, okay, let's go with 8. Okay, and then no, this is fine. Printf ri is equal to, or just and a value, yes, then I, then the register of I. Good, and then put, yeah, end line. So let's try to execute it, and let's see if no, oh, okay, I don't have to run it again. Let's see if everything is as I think it should be. As in, yeah, standard debugging practices. Okay, starting. First we get, this should be 6.1, yeah, this is fine. Now, and the first, after running the first, no, this is before running the first instruction. After running the first instruction, this should be moved to this register. This is correct. Then we actually XOR this register with the content of the third register. The third register is this. And I XOR it. Is it correct? Yeah, it looks like correct. I mean, 1 and 2 XORed is 3. So this looks fine. Then I'm going to load and a value, and the value is loaded, and this is fine. So then I XOR it with the value, and I put the result in VR5. Now, I XOR it. Oh, okay, maybe it is an endianness issue after all, because this is correct, but the endianness is incorrect. The endianness is big endian. Yeah, this is big endian. So KrzaQ, were you right actually? How come? Okay, how do I change the endianness issue without writing too much code? Where is my solver? Here we are. Okay, yeah, you're right, KrzaQ. This is an endianness issue, so my apologies. And this is where I'm going to change it. Perfect. Now, let's run it again. And let's test this key. Yes, perfect. So, KrzaQ was right, I was wrong. That's life for you. And it seems to work, so I can actually comment out this part. Sorry, where is this part? This part's here. Yeah, remake it, make. Run it, test it, run it, test it with a different value. Nope. Perfect. It works. So, what do we do now? Now we look in the application in IDA. So, how does the code actually look like in IDA? Oh, because, well, if we would be given such a binary, we would have to reverse it. Obviously, I'm going to share the code with you and put it on my GitHub. So, don't worry about it. Now, I'm not even asking what this is. This is probably some other. No, I don't have any try-catch blocks, or whatever. So yeah, modern IDA. We can actually click at F5, and we have blah blah blah. Some VM is initialized here, and we enter VM check. And based on the VM check, it actually optimized this a little, it seems. So this is quite funny. Why did it? That's pretty weird what's going on there. Yeah, this is way better. I don't know why. Yeah, so Hexrace is already trying to cheat us. Or make fun of us, I don't know. Okay, this is better. It checks, and there's the check, so let's see what the check is. We know that it has to be, if it's 0, then it actually goes to nope, so it has to be non-zero. We go here, and we get, well, we get, you know, this thing, which is from the argument, from one argument, copy stuff to the second argument. Which is okay, and then we execute this instruction until well, let's see, thinks it's a 4, yeah. And this is what we get to reverse engineer. Now, please keep in mind that we actually have only a couple of instructions, right? So it's not so bad. And here we go with a preview with a minimap. It's not so bad, but obviously there would be more instructions, like apart from the, well, you can count 1, 2, 3, 5, which I implemented, then, or is it 6 actually with the vend instruction, then you'd get a larger this stuff, so sorry, larger function. And having a larger function, it's, I guess, sorry, yeah, makes it more hard to analyze, especially when the C++ stuff starts chiming in, like we see here. So, well, we know it's a vector actually, but if I would compile it with optimized, in an optimized build and without any symbols, this would actually be a call to a weird function which we wouldn't know what's going on there. So it makes it, I don't know, buys a minute. I'm going to be optimistic, it buys a minute. And then you have to analyze it, but in the end the analysis of it boils down to to what? To basically, I don't know what this instruction is. I don't. Oh yeah, to basically finding what instruction is on this position, and it will be similar to probably all the other chunks. Well, here it's, I guess, a little more complicated. Once we would analyze this, oh, here we have XOR. So yeah, as you can see, it's pretty easy to spot, especially the logical and arithmetic instructions. It's a little more work with loading values into registers and storing stuff in memory and so on. But in the end, it's after analyzing it, we still would have to write a disassembler. So let's do that just now. It shouldn't take me too much time to actually write it. I'm not going to use IDA for this. Let's maybe check how it actually. Sorry, before I get there, let's check how it actually looks like if I am going to do this O3 here, and then I'm going to strip it. So make, then strip exa. Okay, and let's look in IDA now. Should be a little funnier. Okay, this is the prologue. Blah 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 blah. Where's the exit? This is probably no. This no. This no. Where's the main? Malloc, string copy. This. Oh yeah. Here's the exit. So this is the exit from main. So this is probably main. Yeah, it looks like the main. So this is the main, and now we go into the check stuff, which, because I already analyzed it, what's going on here? There's way more code. It seems it inlined stuff. And so this is the nope. And it goes here. It actually inlined the virtual machine. This is checking for the opcode, so it inlined the virtual machine, so it makes it even a little more messy to analyze. Though, as we can see, the opcode implementation themselves is much shorter now. This is like, for example, the AND. So it's like from a function which was probably like this big, it actually is now way smaller. So it made it a little easier, made it a little harder, I would say. KrzaQ should be stripped. Yeah, that's exactly as you say. So now let's write a fast, write a disassembler for this, and I'm going to do it in Python. Okay, and this is going to be as easy as I can make it. Byte array from open app.exa, read binary, read it into a byte array, and I'm going to call it D as data. Now, actually in IDA I do need to, sorry, I closed IDA too soon. I actually need to read the, where is my bytecode, right? Because I need to grab the bytecode. So where is it? Here's some memcopy, and the memcopy is from this var. No, this is not it. Are there any more memcopies somewhere here? What's this? Memset. This is probably something else. This is no. The store. No, it's a store, not a copy. Seriously, where is that data? Let's do it like this. No, I need air data. Obviously, this is not it. Maybe it was in data. Yeah, this looks like it. Okay. What is this function? I don't know, but it did look like my bytecode, so I'm just going to use it. So yeah, this is my bytecode, and it's in the file this 2A10. So I actually don't need too much else apart from this. So 2A10. How much do I need? I don't know. I'm going to go with 100 because why not? Okay, now I is equal to 0, while I is less than the length of D. Print. Yeah, X is fine. Do I really want to print here? Yeah, it can be a print. Okay, now I need to grab the instructions. So, is there a smart way to do it? Do I care about a smart way? I don't care about a smart way, I guess. Let's do it hacky way. So if d of I is equal to, and we start going through, again, I'm not going to reverse engineer it, so I will just go with my, with this thing here. Okay. So if it's equal to 0, then this is probably an XOR. So print the XOR, and I do need the register numbers here. So VRI with the register numbers are going to be obviously +1, +2. Now this assembler can be hacky because it's actually a simple bytecode, right? If it would be anything more complex, I would have to write a proper disassembler here, more the like of which I created in my last live stream. Or there's a good question: what is the advantage of using a byte array? So the byte array is actually can be treated. It's basically like a uint8 array in C or C++, which means if you do something like this, it's actually going to return you an integer, not a character. Without it, it would be just a string, and therefore it would be returning a character. So I would have to do, for example, ord to get the ordinal value of the character. That's why I like to do it. And I add, 3 here. Then I know I need at least a couple of instructions more like this. Now, this is going to be the end. This is going to be VOR. Then I have this one, which is move. And then I actually do have the end, which is the end. And it doesn't, it just break. I'm going to break here. Okay, now I'm still missing one more instruction, right? So I'm still missing the 10th instruction, which is vmove I, which actually gets an immediate value, and I want it represented as hexadecimal. So let's do it here, and this actually will not cut it. I'm going to do rd struct unpack I, and then I need I plus 2 plus 4 here, which is fine, and 0. Okay, now are my lengths correct? No, this length is not correct by any means, and the rest is fine, so let's see how it goes. Python, how is it called, this? And this is supposed to be our code, but it didn't display too correctly because I failed somewhere. Where did I fail? Because like for some reason it didn't output here. Like, where's the address? Why didn't you put the address there? Oh, I know. Right. Because I'm not continuing it, and it's just, that was quite an interesting mistake. Yeah, this is fine now. So this is like a short, fast, and hacky disassembler, and let's compare it with our functions. So what do we have here? Yeah, This is okay, 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 okay. This is fine, okay. Okay, 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 and I need to scroll down, so, and, okay, yep. So, as you can see, actually, writing a disassembler for a custom architecture took me, what, 5 minutes, right? So, this is basically the amount of time I would buy using this implementation. I would buy the 5 minutes of writing the disassembler, and I would buy whatever time is required to actually analyze the virtual machine, which is for somebody who knows what they are doing, it would be, I don't know, like 5-10 minutes, maybe 15. So yes, that's actually it. So this is the most basic virtual machine you can implement. You can obviously have some more fun with it. I did mention already at the beginning of the stream the return-oriented programming virtual machine, which actually had a virtual machine there. Apart from it, with with Mateusz Jurczyk, we created another KrzaQ with a different virtual machine where it was actually more funny because each of the implementation of each instruction was actually placed in a different segment. Like think of x86 32-bit segments, because you could, on Windows, that's for Windows, you could actually register segments. So there's that, and therefore actually disassembling it didn't give you too much information, and most debuggers, apart from WinDBG, failed totally when they saw segments. They didn't know what to do with segments. So there's that, and we also made it a little funnier because after executing each instruction, we would randomize the bytecode. So having an instruction at this at this address and executing the next one, even if it would be the same opcode, exactly the same opcode, it would be a different instruction which would be executed in the VM. And it wasn't really randomized. It was, you know, a pseudo-random number generator, which we knew the sequence for when generating or compiling the code. And yeah, I think 2 people solved it in the end. The KrzaQ pseudo is still solvable, but it did take some time. And I guess that's it for today. So if you have any questions, it's a good time to ask them. Otherwise, we'll be finishing early today. If you have any ideas for what the next stream topic could be, please let me know. One idea is, for example, to, you know, go with implement a more sophisticated virtual machine for anti-reverse engineering, though it's kind of more of the same. So, so yeah, if you have any good ideas, then just let me know. Apart from that, I would like to thank KrzaQ for being my moderator today, and I would like to thank Foxtrot Charlie for preparing the mission, which you will get to see in a second. So that's it. Thank you very much for today and for being here, and see you next week. Oh, there's a question. Just in time. There's a good, talented, very good, talented people here. How about making a Reddit? Doing a subreddit is an interesting idea. That being said, I'm going to say no, because at some point, hopefully sooner than later, I do hope to have that our live stream will get a website and there will be a forum there. So, but it's an interesting idea. I actually didn't think about it. So it's a weak no, not a strong no. Cool. Okay, that's it. So again, thank you. See you next week. Happy hacking and happy programming, and have a great one. So see you